How much of the cosmos has already died? At first, this seems like an impossible question to answer. Aside from rare cosmic explosions, the universe on the grandest scale seems frozen in time, a silent picture from an unimaginably long story. Yet a Swedish physicist named Eric Holberg decided he wanted to understand more. While his name is not widely known today, in 1940, inside a darkened Stockholm gymnasium, he conducted what might be one of the most brilliant experiments since the days of Galileo. In doing so, he became the first person to watch millions of years of cosmic history play out before him. His concept was elegantly simple. He and his students set up 74 stations across the gym floor. Each station had a bright lamp and a light sensor to measure the illumination it received. These stations represented pieces of a galaxy, individual bits of mass that could both influence and be influenced by their surroundings. The light stood in for the force of gravity, weakening with the square of the distance. He arranged the stations into two groups, sketching the rough shapes of two spiral galaxies just before they collided. Then, slowly and methodically, he set the lamps in motion. He measured the light at each point, using that data to calculate where that piece of the galaxy should be moved, as if 1,000,000 years had passed. He repeated this process over and over. Holberg had built the world's first cosmic simulation using an analog computer. Watching galaxies evolve before his eyes, Holberg saw stunning beauty, the graceful stretching and the elegant arcs of tidal tails created during a merger. But he also witnessed something else, laid out with lamps and sensors on a gymnasium floor. He saw how galaxies die. Holberg observed a universe that is not static. He saw that the vibrant cosmos we know, filled with galaxies arranged in a grand cosmic web, will not last forever. Billions of years ago, the universe was dark before the first stars ignited, and due to the relentless expansion of space, there will come a time in the far future when the cosmos returns to that darkness. In his shadowy gymnasium, Holberg glimpsed that impermanence. What he could not see, lacking more advanced tools, was that the wider universe was already far along the path to oblivion, well past its prime. Today, following Holberg's pioneering work, we combine sophisticated computer simulations with detailed observations to learn a startling truth. A vast portion of the universe is already dead. We are living in a cosmic twilight. The long future holds nothing but decline. In a way, this is a story of betrayal. In a changing universe, the very forces that spark star formation eventually turn against their creations, killing them from within. 4.5 billion years ago, shortly after its formation, our Earth was a literal hellscape. The young planet rumbled constantly as its crust shifted and cracked. Molten rock flowed over a landscape in perpetual motion. Surface temperatures soared to 1,000 degrees. The atmosphere was barely present, its composition not much different from the solar nebula from which it formed. And in the sky above this chaos was the moon, but not the moon we know, appearing 15 times larger than it does today and glowing a dull red. This young satellite would have dominated the horizon like a dreadful omen. So what happened between then and now to give us the calm, distant moon we see today? It is very slowly moving away. We know this from lunar laser ranging, a technique where scientists fire laser pulses at the moon and time their return. The accuracy of these measurements was greatly improved by reflectors placed on the lunar surface during the Apollo missions. Scientists have calculated the moon is receding at about an inch per year. It would only complete its journey in roughly 15 billion years, long after our sun will have consumed the Earth. Our night sky is far from unchanging. On cosmic scales, our retreating moon is just a minor example. Our entire universe is in a state of constant transformation, on both vast and minute scales. Indeed, Renaissance astronomers were amazed to discover the heavens were as tumultuous as life on Earth. Once they realized the Earth itself moved, the idea of a permanent, fixed cosmos collapsed. Comets were found to be not atmospheric phenomena, but visitors from the outer solar system. The bright guest stars that flared in the night were actually the deaths of massive suns. Nebulae were not mere clouds, but either the birthplaces or graveyards of stars. The universe was revealed to be in constant flux. Because of this change, there are things that have not yet had time to be born, and things whose time has passed, things we will never see again. The infant universe was profoundly different from today. Immense energies may have forged exotic particles like magnetic monopoles or strange structures like cosmic strings. They are all gone now. There was a brief period when the universe itself could create new elements. Primordial hydrogen and helium condensed from a thick nuclear soup within minutes of the Big Bang. Generation after generation of stars lived and died, forging heavier elements and enriching the cosmos, eventually leading to planets, oceans, and the complex molecules of life. But all the hydrogen the cosmos will ever have was formed in roughly a dozen tumultuous minutes just after the universe began. There was a time when the cosmos was completely unrecognizable. About 380,000 years after the Big Bang, the universe was in a distinct state of matter. The cosmic gas was over 10,000 Kelvin, hot enough to be a plasma. When the universe transitioned from that state to something more familiar, it released a flood of radiation, a one-time event that created the cosmic microwave background we can still faintly detect today. That will never happen again. There was a time before stars, before galaxies, before planets. There was a time when the first stars shone, colossal suns that seemed to have vanished entirely from the modern cosmos. There was a time when the universe was flooded with new stars and chaotic, colliding galaxies. That time is now over. This story of cosmic change began with Edwin Hubble's discovery that galaxies are moving, and most are moving in one direction, away. The universe was expanding. This was key. In a static universe, everything would be the same. No matter where we looked, we'd see the same kinds of galaxies, the same activity, the same structures. That is not what we found. Hubble also dramatically expanded the known size of the universe. Before him, many thought the Milky Way was all that existed. His measurements of distant galaxies blew the universe up from 300,000 light-years across to 280 million light-years. Through the first half of the 20th century, estimates continued to grow as telescopes improved, reaching over 4 billion light-years by 1955. Then, in the late 1950s, the first radio surveys of the sky shattered all previous estimates. Physicists discovered strange, intense points of radio emission, calling them quasi-stellar objects, or QSOs. The name was later shortened to quasars. They turned out to be incredibly bright, compact sources of energy that could outshine 1 million galaxies at once. Crucially, there were no nearby quasars. They were all billions of light-years away. Once again, the universe ballooned in size. The most distant quasar found in the 1960s was 12 billion light-years away. The furthest we see today is closer to 13 billion light-years, existing a mere 600 million years after the Big Bang. Quasars were creatures of the distant past, active only in the young universe. In a static cosmos, we'd expect to find quasars nearby, but there are none. We must conclude the universe was different in the past, with conditions that no longer exist. This change is driven by the universe's expansion. But that's not all. We've discovered it's not just quasars that are different, but galaxies themselves. Observations from the James Webb Space Telescope reveal a youthful universe filled with smaller, dimmer galaxies than the grand spirals and ellipticals we see today. One of the earliest found, known as Jade's GSC 14-0, is from about 282 million years after the Big Bang and is bursting with newborn stars. 5 billion years. Deep cosmic surveys find that the grand cosmic web, the large-scale structure of the universe, took time to evolve from diffuse gas into the intricate lattice we see today. A changing cosmos tells us the universe has a finite age, but its endless expansion also means something else. The universe will die. In fact, it is already well on its way. We take the known laws of physics, program them into a computer, set initial conditions from an early cosmic epoch, add all the ingredients we know, and let it run. Eric Holberg was the first to recreate the cosmos in a lab, but he was far from the last. 80 years later, gymnasiums have been replaced by supercomputers, and light bulbs by complex simulations. One of the largest, created by Volker Springel and Lars Hernquist, and called Illustris TNG, uses nearly 100,000 computer cores working together to simulate just a tiny portion of the visible universe. Their code can follow gas as it turns into stars and trace the formation of cosmic structure. A primary goal of Illustris TNG is to understand the detailed mechanisms behind the rise and slow decline of galaxies. Observations from the James Webb Space Telescope show galaxies first appeared within a few 100 million years of the Big Bang. They were initially small, less than 1% of the Milky Way's modern mass, and relatively dim. But these first galaxies grew quickly, feeding on surrounding material. Simulations like Illustris TNG show us what observations cannot: the hidden flows of gas onto galaxies and how they mix to form stars. Things moved slowly, not with a crash but a whisper, secret movements in the dark, a conspiracy of gravity and slender threads of matter. The universe was young then, only 100 million years old, a fraction of its current size, and all was darkness. The fires of nucleosynthesis that created the first elements were a dim memory. Over time, faint, diffuse clouds found each other. Their growing gravity pulled on their surroundings, drawing material closer. Then, in some unknown region of the vast, cooling cosmos, the first spark was lit. Primordial elements, crushed by their own gravitational weight, ignited into fusion. It was the first release of energy in 100 million years, the first new light to shine on the universe. Change had come. The cosmic dawn had broken. But those first stars were not finished. Clumps of gas and newborn stars gathered together, huddling for warmth against the cold, dark universe. More gas piled onto these safe havens, these refuges, these cities. Starting as simple spheres, they flattened into disks. Then, as gravitational perturbations worked their way through them, dazzling spiral arms of starlight emerged. The first galaxies were born, and they would come to dominate the visible universe. One of the best places to view the night sky is in the deep desert, far from light pollution. The Atacama Desert in northern Chile is one such special place. Stretching hundreds of kilometers along the Andes, this high, rugged desert offers world-class observing conditions. There, once your eyes adjust to the darkness, you can see up to 3,000 individual stars with the naked eye. It's the ideal location for a telescope array. The Atacama Large Millimeter/Submillimeter Array, or ALMA, sits 5,000 meters above this bone-dry desert. It is an interferometer, a collection of 66 individual dishes working together to peer deep into the sky. In 2015, Japanese astronomer Hideki Yumehata used it to find a set of proto-galaxies. He mapped the SS At-22 protocluster, a monster in its cradle of filamentary matter nearly 12 billion light-years away. As galactic nurseries go, SS At-22 is gigantic, spanning over 200 million light-years. Individual gas bubbles carved out by the infant galaxies are each 400,000 light-years across. It was one of the first such proto-clusters to emerge, and ALMA brought us right into the delivery room. Yet within a mere 3 billion years, these galaxies would begin to collapse. But for a time, they were truly glorious. As galaxies first grew, the gas pervading the universe fractured and collapsed into filaments and sheets. At the nodes where these filaments intersected sat the newly built galactic cities. Each growing galaxy was connected to the wider universe by numerous umbilical cords, drawing resources from its surroundings to grow and produce stars at an astounding rate. 5 billion years after the Big Bang, galaxies produce stars over 10 times faster than they do today. If intelligent beings lived on planets in that young universe, they wouldn't need a telescope like ALMA to witness stellar miracles. They could simply look up. Our sky is dominated by the light of only the largest stars. Stars like our sun are too dim to see across interstellar distances with the naked eye. But if you took that same view back to the era of peak star formation, you would see over 30,000 stars, perhaps more. This era is known as cosmic noon, the peak of the universe. It was glorious, but it wouldn't last. Our modern universe is different. Star formation happens only in select sites where conditions are right, like the nebula NGC 346, a star-forming cluster in the Large Magellanic Cloud. Otherwise, most galaxies are quiet, sleepy places. Even our own Milky Way creates only about 7 new stars a year, just 7 across its entire 100,000 light-year expanse. In an entire human lifetime, only around 500 new stars will awaken within our galaxy. Astronomers consider the Milky Way relatively active for our time. So what happened in the roughly 10 billion years between cosmic noon and now? Why is the universe so much less fruitful today? Hastily built, the early galaxies were small and inelegant. They hadn't yet formed grand spiral arms or settled into a stately equilibrium. Titanic forces competed within them like rival factions fighting for control. Material drifted in from all directions, but most rushed along the filaments connecting each galaxy to the broader cosmos. As new gas rushed in, gravitational perturbations triggered the collapse of nearby gas clouds. Those clouds, once destabilized, would fragment into hundreds or thousands of star-forming clumps at once. The first rounds of star formation were the focus of the JADES survey using the James Webb Space Telescope. The team, co-led by Marcia Reek of the University of Arizona, searched for what amounted to tiny smudges of light. Yet those smudges represented millions or billions of newborn stars lighting up simultaneously. When those stars died, they exploded as supernovae, sending shockwaves through their neighborhoods. Round and round the feedback cycle went as new material led to new star formation. Each galaxy was a picture of turbulence, and not just internally. Many early galaxies didn't just gather material quietly. Sometimes they stole it from each other. The CANDELS survey was designed to watch this cosmic drama unfold. The largest project the Hubble Space Telescope ever undertook. It used about 60 days of observing time between 2010 and 2013 to provide deep images of over 250,000 galaxies. The young universe was smaller, with the average distance between galaxies far shorter than today. As these galaxies grew, they battled over resources. Galactic interactions aren't always slow, gentle dances. Sometimes they involve complete consumption. Our own Milky Way hides many remnants of its violent history. To a casual observer, one population of stars looks much like another. But thanks to enormous catalogs of billions of stars gathered over the years, careful astronomers have teased apart these populations, deducing which stars were born in the Milky Way and which are later arrivals. These investigations have revealed dozens of merger remnants. Some recent ones are still partially intact, like dense cores we call globular clusters. Some are stretched and elongated, like the Sagittarius stream, distorted by the Milky Way's mighty gravity. Others are completely assimilated, their stars scattered widely within the galaxy, like the entertainingly named Gaia sausage. Each of these encounters, mergers, and collisions led to fresh rounds of star formation. When a larger galaxy consumed a smaller one, it was cannibalism. But when galaxies of equal size met, it sparked a period of star formation unlike anything either had seen before. In the most intense cases, the gravitational interactions in a merger could create stars over 1,000 times faster than the Milky Way does today. Perhaps the most crucial ingredient, the central player regulating star formation, the key component determining how efficiently early galaxies turned gas into stars, was dust. Humble, simple dust. Today, dust is everywhere in the universe. These are tiny, usually microscopic grains of various chemical compounds. It's so abundant you can even see it. Diffused dust in our solar system causes the zodiacal light. If you look to the western sky shortly after sunset on a clear, dark night, you might see a faint glow stretching from the horizon, sunlight scattering off dust between the planets. So much dust exists that Earth gains several tons of mass each year simply by moving through it. Dust plays a vital role in star formation. To make a star, you can't just bring together a reservoir of gas. It would sit as a nebula for millions of years because the gas is hot, and its temperature prevents collapse into the small sizes needed for a star. But dust can cool a nebula by efficiently emitting radiation. By cooling through dust, a gas cloud can continually contract until its central density reaches the critical threshold to ignite nuclear fusion and become a star. The extremely young universe was completely devoid of dust, as only hydrogen, helium, and trace lithium and beryllium were made in the Big Bang. This is one reason we don't fully understand how the earliest stars formed. But once those stars lived and died, they enriched their surroundings with heavier elements. Those elements quickly mixed to create the first dust. Observations with ALMA reveal a dusty early universe, with small galaxies obscured by relatively thick hazes. All this frenetic activity meant more stars were produced in the first 3 billion years after the Big Bang than in the 10 billion years since. Cosmic noon was the peak, the zenith of star formation. Then it stopped. Cosmic noon gave way to cosmic afternoon. Today, in the modern universe, we are in cosmic evening. Galaxies continued to form. They grew larger and more massive. The modern Milky Way is 10 times bigger than it was at cosmic noon. Galaxy building continues even now, with dim clumps of gas still emerging into small galaxies. But the pace is much more sedate, much more measured. His studies laid the groundwork for understanding a certain type of galaxy, with profound implications for cosmic evolution and the ultimate fate of everything. With the right setup, Holberg could have recreated Mate 7. When astronomer Charles Messier published his famous catalogue of deep sky objects in 1781, he had no idea that number 87 was different from the others. In fact, he wasn't particularly concerned. Messier had one thing on his mind. He really liked comets. To quote French astronomer François Arago, at a time when he was in expectation of discovering a comet, his wife took ill and died. While attending upon her, being withdrawn from his observatory, Montaigne anticipated him by discovering the comet. Messier was in despair. A friend visiting him began to offer some consolation. Messier, thinking only of his comet, exclaimed, "I had discovered 12. Messier was an avid comet hunter. To avoid confusing fuzzy objects in the sky with comets, he created his catalogue of things that were definitely not comets. And Mate 7 was definitely not a comet. Mate 7 was, and still is, an elliptical galaxy. And Mate 7 was not just any elliptical galaxy, but a true leviathan containing several trillion stars. Even with a backyard telescope, you can tell it looks different. There is no flattened disk, no majestic swirl of spiral arms. This is because Mate 7 is different from the Milky Way, different from most galaxies around us. Mate 7 is dead, a graveyard of galactic proportions. Billions of years ago, it blazed with activity, producing hundreds of new stars each year, but not anymore. Among astronomers, elliptical galaxies like Mate 7 have a nickname, the red and dead galaxies. Stars still exist there, but not like before. They are mostly small dwarfs, dim and red, only a fraction of the sun's luminosity. Among those clinging to feeble life lie the bones of their ancestors. Black holes, places of infinite gravity and no escape. Neutron stars and white dwarfs, leftover cores once capable of fusion, now slowly cooling. And finally, the oblivious planets, asteroids, and other debris of once magnificent solar systems. Hundreds of billions of red and dead elliptical galaxies like Mate 7 are scattered across the cosmos like rotting corpses left after a great battle. Between 20 to 30% of all galaxies are ellipticals. Yet, because they can grow so massive, Roughly 40% of all stars in the universe call an elliptical galaxy home, and soon enough, their numbers will grow. It is the fate of every galaxy in the universe. Even our own Milky Way, as calm and steady as it has been for billions of years, will someday become one of these red and dead galactic graveyards. Just as astronomers don't fully understand what caused the great rise in star formation in the early universe, they don't yet know exactly how galaxies die. But observations of dead galaxies show it's usually not one single culprit, but a series of events that strangle a galaxy of newborn stars. These culprits are not new processes, but the very same ones that initially drove rapid star formation. In other words, galaxies seem to be victims of their own success. Astronomers use the term quenching to describe the death of a galaxy, processes that extinguish star formation, relegating the galaxy to the collection of the red and dead. Many mechanisms can participate in quenching, and their importance varies from galaxy to galaxy. But in the end, all galaxies share the same fate. Sooner or later, some process goes out of control and snuffs out star formation. Sometimes it's simply a period of too intense star formation. During these periods, thousands of giant, bright stars can appear at once. These stars pump out enormous amounts of particles and radiation, creating stellar winds alongside their high-energy starlight. These winds, stronger than any hurricane but so thin you wouldn't feel them, can combine to sweep through galaxies, heating the interstellar gas. When the gas is hot, it can't cool, collapse, and form stars. Sometimes stellar winds are so strong they drive material out of the galaxy altogether, stopping accretion in its tracks. Loosened from the galaxy's gravitational grip, that material can no longer participate in star formation. This process of galactic expulsion is amplified when supernovae explode. Since clusters of massive stars tend to be born together, they have similar life cycles and often die as a group. When hundreds or thousands of supernovae explode nearly simultaneously, they launch massive plumes of material that blow holes in the interstellar gas, like the local bubble our solar system is sailing through. In 2016, a team led by astronomer Artie Camps-Farina went searching for these explosive events. After weeks, they found a beautiful sight, a series of 3 bubbles surrounding the Triangulum galaxy M33, nested together like Russian dolls. Even the mechanisms that lead to accretion can quench a galaxy. As galaxies drift through the intergalactic medium, they enjoy a steady supply of infalling material that gently rains down, refilling their reservoirs of star-forming fuel. Galaxies aren't moving randomly. They are drawn toward each other and toward larger clusters. In the modern universe, clusters are home to 1,000 galaxies or more, bound by mutual gravity. Winding through those galaxies is a hot plasma. This plasma is so thin it would register as a vacuum in Earth labs, but it still plays a role. When a galaxy enters a cluster, it encounters this hot gas. The galaxy's motion through the gas heats the material within the galaxy itself, shutting off new star formation. Additionally, friction between the cluster gas and the galaxy's gas can rip material away. Astronomers can see this happening now. They observe long tentacles of gas streaming behind these galaxies. Astronomers call them jellyfish galaxies. Once again, the twin effects of heating gas and removing it can quench a galaxy, turning it from blue and bright to red and dead. But arguably the greatest galaxy killer isn't supernova winds or merger friction. Instead, it is the black heart at the center of almost every galaxy. When we look at red and dead galaxies in radio wavelengths, we can see long, thin jets of intense radiation piercing thousands of light years through the galaxy. When the Event Horizon Telescope trained its globe-spanning instrument on the center of MADI 7, it captured the shadow of an enormous supermassive black hole. A black hole surrounded by a disk of intense radiation. A jet of energetic particles reaching thousands of light years, and an empty ghost town of a gigantic galaxy. It looked like a crime scene with the knife still in the victim and the villain hiding in the shadows. Supermassive black holes, with masses exceeding 1 million suns, appear very early in cosmic history. Some observations suggest just a few 100 million years after the Big Bang. This means the story of galaxy evolution is intertwined with the story of black hole evolution. Like a dark secret, a galaxy tries to hide its whole life, a secret that ultimately destroys it. For the most part, the rest of the galaxy doesn't notice the central black hole. While massive, it still weighs less than 1% of the galaxy's total mass, except when black holes awaken. These are the quasars, the same intensely bright objects astronomers noticed in the 1950s that cemented our understanding of a changing universe. Soon after quasars were discovered, Fred Hoyle suggested supermassive stars might power them with their intense gravity. Richard Feynman pointed out such gigantic stars couldn't support themselves. Eventually, astronomers realized it must be a black hole at the center. Despite Hoyle's idea not gaining wider acceptance, his chosen name stuck, and they became known as supermassive black holes. When matter, a gas cloud or a wandering star, comes too close to the central supermassive black hole, its extreme gravity shreds it, forming the material into a thin disk. This accretion disk reaches temperatures of trillions of Kelvin, emitting a flood of high-energy ultraviolet and X-ray radiation that rushes through the galaxy. Quasars powered by supermassive black holes don't just heat a patch of interstellar gas. They can inflate an entire galaxy, puffing it up like a hot air balloon. The heated gas cannot collect, condense, fragment, or form stars. It can only drift aimlessly in a superheated, ionized state. In moderation, an active quasar can be beneficial. It can slow star formation, preventing a galaxy from using all its gas at once. In this way, the central black hole, despite its relatively small size, plays an outsized role as a critical regulator, keeping a galaxy running efficiently. But when a quasar gets too bright, it can destroy a galaxy from the inside out. This typically happens after a major merger. When galaxies of equal size merge, their twin black holes quickly find each other and merge. This unified black hole moves to the center of the new galaxy and feasts on the surplus of material crashing around it. Once this quasar activates, it heats so much gas that it doesn't just slow star formation, it stops it completely. So much material is expelled that only a feeble trickle remains. The quasar has one more trick: the jet. The ferocious energies of the accretion disk generate enormously strong magnetic fields. Some accreting gas follows these magnetic fields, twisting in corkscrew paths around the black hole and emerging as powerful jets racing out from the poles. Particles in the jet are accelerated to nearly light speed, and magnetic fields keep the jet straight and narrow for tens of thousands of light years. Any material in the jet's path is shoved out of the galaxy entirely, never to participate in star formation again. This was the smoking gun that killed Matey 7. Too many mergers and an overeager supermassive black hole. Not all galaxies will die through merger. Some will be lucky, distant enough from neighbors to escape that fate. But even if they keep producing stars for eons, eventually their lights will dim too. The universe is still changing, still expanding, still pulling galaxies apart on average. There is only so much material available. Slowly, ever so slowly, all galaxies will simply run out of gas. In this sense, galaxies are temporary creations. They will live far longer than the current age of the universe, but they still have a finite lifespan. While cosmic noon, the peak of the universe, came and went in the blink of a cosmic eye, a mere 3 billion years after the Big Bang, cosmic evening and cosmic twilight will last much, much longer. The automated system awoke the astronomer. She roused herself methodically from deep slumber, in no rush. Checking the chronometer, she had been asleep for over 140,000 years. The analysis could wait until after coffee. Her station was remote, as all such stations were. It was on the surface of the moon once known as Titan. Long ago, it had cooled and solidified, losing its oceans and atmosphere. It still orbited what remained of Saturn, which in turn orbited the black dwarf sun, now with a temperature just under -170 degrees Celsius. The cache of antimatter powered her station and would continue to do so for a long time, more than enough to chart the end of the universe. There was no larger purpose to this mission. She knew the recordings she kept, the notes she diligently took, would ultimately be read by nobody and would in time dissolve along with all other microscopic objects. So the astronomer worked, sifting through the meager data collected by her observatory outpost. And there it was, exactly what she had hoped for. After several million years of false positives, this was something. A new star had been born. It was small, a fraction of what the sun once was, but it was still a star. Its formation had been triggered by the random collision of two brown dwarfs, giving the new entity just enough mass to reach critical fusion densities in its core. After completing an all-sky scan, she added the new object to her log. In total, there were now 78 stars shining in the Milky Way galaxy, the highest number in over 1 trillion years. Content, the astronomer returned to her stasis chamber to await the next signal. The far future universe would be utterly alien to us, accustomed as we are to planets, oceans, living suns, and star-filled skies. But in the end, darkness will come for us all. As we know, the universe is expanding. That expansion has driven cosmic change, from a hot, dense plasma to a cool gas, from a thin soup of hydrogen to pockets of star formation, from the dark ages to the glory of cosmic noon. 8 billion years old in its twilight years, star formation peaked long ago. While galaxies have continued to assemble and grow, their total brightness has already begun the long, slow decline into oblivion. Hastening this decline is dark energy, the mysterious substance causing the universe's expansion to accelerate. We don't know its true nature, cause, or ultimate evolution. But if it continues as it has for over 5 billion years, the fate of our cosmos is sealed. Accelerated expansion drives everything apart, starving galaxies of the material needed to build new stars. Given enough time, it will pluck stars, planets, and remnants from galaxies one by one, dissolving them. The grimness of this fate is offset by its longevity. When we discuss the universe's timeline, we find we are still in its infancy. What we perceive as a decline from cosmic noon is just the brief initial flash that set the stage, putting all the pieces in place for the cosmos to live a long life. In those distant times, when the universe is orders of magnitude older than now, new wonders will appear, strange phenomena we can't possibly fathom in our youthful present. In 100 billion years, the observable universe will disappear from view. Any galaxy not already bound by gravity to our local group will be caught in the accelerated expansion of dark energy and pulled away faster than light until it vanishes. By that time, a new kind of star will emerge in the Milky Way, one we don't see today because the universe isn't old enough. The largest stars will be long gone, as will almost all sun-like stars. Instead, our galaxy will be dominated by red dwarfs. As they evolve, they will gain temperature, becoming blue dwarfs, small, dim, but bright blue jewels set within the galaxy. At the same time, the cosmic microwave background, our key observation of the universe's birth, will become so redshifted and cold it will be impossible to detect. In this strange new reality, another kind of star will appear for the first time. Today, stars have a fundamental lower mass limit set by the need to achieve fusion in their cores. But far in the future, the galaxy will be so enriched with heavy metals that it can lower the temperatures and masses of possible stars. The smallest stars will be so diminutive and cool that their outer surfaces could have temperatures below zero. Encased in clouds of ice, these frozen stars will be barely detectable, but they will exist. Sometime between 10 and 100 trillion years from now, the last star will be born. By then, the universe will be more than 10,000 times larger than today. In what remains of the galaxy, brown dwarfs will occasionally collide, reaching the thresholds needed to become red dwarfs. But that will be the end of stars as we know them. Some 10 to 20 trillion years after that, the last star will go out. In the ensuing eons, the galaxy will continue to dissolve. By 10-15 years, our sun, long cooled to a black dwarf, will have a temperature only 5 degrees above absolute zero. Through gravitational interactions, all planets will have detached from their parent stars and been flung into the abyss. By 10-30 years, all macroscopic objects will have either detached from the galaxy or fallen into the central supermassive black hole. By this time, all macroscopic objects will be solitary, each in its own pocket of the universe. By 10-100 years, all black holes will disappear through Hawking radiation. Starting around 10-1000 years from now, even black dwarfs will die, exploding in supernova detonations as they lose their electrons, lowering the limit for catastrophic collapse. Finally, around 10-1500 years, perhaps the last kind of star will appear on the cosmic scene. Though, due to dark energy's accelerated expansion, there will be no observers to witness it. A form of cold fusion moderated by muons will convert all planetary mass objects into solid spheres of pure iron. These are iron stars. They will not glow, except from the feeble heat of their temperature a shred above absolute zero. But they will persist. For how long is anyone's guess? One estimate suggests that some 1076 years from now, all objects will dissolve through quantum tunneling, even the iron stars. Beyond this point, all molecules, atoms, and nucleons will disappear. The universe will be a thin soup of subatomic particles and radiation, separated by vast expanses of nothingness. And the decay leading to this cold, empty cosmos has already begun. If you found this journey through cosmic time fascinating, please show your support. Liking this video helps others discover it. Subscribing ensures you don't miss our next exploration, and sharing it spreads the wonder. Let us know your thoughts in the comments below. Thank you for watching Atomic Particles and Radiation, separated by vast expanses of nothingness. And the decay leading to this cold, empty cosmos has already begun. If you found this journey through cosmic time fascinating, please show your support. Liking this video helps others discover it. Subscribing ensures you don't miss our next exploration, and sharing it spreads the wonder. Let us know your thoughts in the comments below. Thank you for watching.